Hi, welcome to the second lecture in the Stern-Gerlach experiments. We're going to be covering 4 conceptual experiments now based off the Stern-Gerlach experiment we discussed last time. Basically, the point being these experiments highlight some of the quantum weirdness and aspects of quantum mechanics that we're going to probably spend a lot of time trying to figure out why they work that way to really understand how to use quantum mechanics. Last class, just to recap, we covered the original Stern-Gerlach experiment, which showed the quantization of angular momentum, and we also discussed the failure of classical mechanics to explain this. So just a quick reminder, the Stern-Gerlach experiment involved an oven that a collimator that created a beam of neutral silver atoms that were then shot through a magnetic field gradient that exerted a force on those atoms and split the beam into 2 distinct beams. One went up, one went down, and it showed that the quantization of this angular momentum. We tried to analyze this using classical mechanics and all the types of angular momentum that could create these magnetic moments that we could think of, and it failed. In classical mechanics, essentially the oven would create a randomized orientation of any magnetic moments, and we would expect that force due to the magnetic field gradient would just sort of push that beam up or down based on that orientation. But since it was random, we would expect that beam just to kind of be smeared out in the z direction. But what was shown was by Stern-Gerlach was that it actually split into 2 beams. And quantized that angular momentum into up or down. Turns out that this type of angular momentum that we're talking about is what we refer to as spin angular momentum, or the intrinsic angular momentum of these particles. It's called spin kind of because I think one of the first ways people tried to think about it was that it was a ball of charge spinning. An electron was a ball of charge spinning. But that is not what's actually going on. Electrons are not balls of charge that are spinning. We want to be thinking about spin, or the intrinsic angular momentum, as just a fundamental intrinsic property of these particles, not that something that's derived from the behavior of the thing. So think of it the same way you think about charge. Electrons have a negative charge, protons have a positive charge. Particles will have a given spin, just an intrinsic property of that particle. We also mentioned that the value of that spin angular momentum, the 2 values that it could have when that split beam was showing, is plus or minus h bar over 2. So the ones that went up, we call them spin up, plus h bar over 2, and the spin down, negative h bar over 2. One final note on the Stern-Gerlach experiment, there is nothing special about the z direction. We could have aligned our magnetic field gradient along any direction we really wanted. We could have switched the setup so it was aligned in the x direction. We would have got the same result. It would have split the x component of that angular momentum into 2 values, plus or minus h bar over 2. Likewise, if we did it in the y direction, there's no particularly special spatial orientation in this. So what we're going to do today is we're going to look at the SPINS virtual labs. You can go to the syllabus or the course webpage and get info on how to get access to this software. There's an online version. You can also download a local version to run this. We will be using this in some of our synchronous meetings to do some activities together and really get comfortable with quantum mechanics and some of the subtleties with it. But anyway, so see those resources on how to get it, because you will need it for yourself. In the meantime, we'll just walk through it. So this is what the Stern-Gerlach experiment looks like in the SPINS virtual lab, right? So it's just take away all the complexities of creating a magnetic field gradient and all that, and just give the sort of core concepts that are needed. We need an oven that produces a beam of particles. We need a Stern-Gerlach analyzer. That's what this thing is. It can be aligned. You can change this from the z direction that it's in now to the x or y direction, or even an arbitrary direction n. And that just basically splits the beam into 2 paths. The last thing we need are these counters. They're exactly what they sound like. They just count the number of particles that get to each counter, right? So we put a counter here. In this sort of setup that we're looking at, it was standard Stern-Gerlach, beam of particles going into the Stern-Gerlach analyzer, splits them into the two paths. 50 went up, 50 went down. It was evenly split. Little brief bit about notation. We label the quantum states of these beams with what are called kets. They're these things that look like this. For the general state coming out of the oven, we're labeling that just with a generalized ket, typically the psi symbol inside the ket. Coming out, there are two possible values of the spin in the z angular momentum. It can be spin up, which we label with this plus sign. So spin up in the z direction is a plus ket. Spin down in the z direction is a minus ket. And we'll discuss that more in the next video when we go through how to mathematically sort of analyze these, quantitatively analyze some of these experiments. But for now, we can just sort of conceptually use them to sort of label what the states are of these particles as they go through. So now if we open the Stern-Gerlach, the experiment, if we look at that in the spin software, we have the same sort of setup that we had before. We have the oven, we have the Stern-Gerlach analyzer, and two counters set at the two outputs, those two beams that would come out of that thing. And I can send a particle at a time through this thing, and you'll notice as we go through, it just sort of, the particle goes to one of those things, and it does so in a random manner. And slowly we'll count them all. And the more you do, I can do 10 at a time, 100, 1,000, whatever. And what we end up seeing is roughly half go up, half go down. And that's what the Stern-Gerlach experiment saw. We saw a splitting of that. Now, another thing I can do is I can add a second Stern-Gerlach analyzer here. And if I bring that there, and then I take this beam from the spin-up output of the first Stern-Gerlach analyzer and send it to the second Stern-Gerlach analyzer, add another counter, and bring that over here, and then just count the numbers out of there. What we can see is as I send particles through this, I send one, spin down, send two, three, it goes up, and we get essentially what you might expect. So if I send, let's say, 1,000 particles through that, half out of the first Stern-Gerlach analyzer were down, the other half went up, and were analyzed again, and that spin up beam was then measured as whether it was spin up or down, and we get sort of exactly what we might expect classically, where all the beams from the spin up beam, when measured again, were spin up again. Now, one thing I want to notice, this experiment could have been totally flipped. So if I reset that and I sort of bring this, the Stern-Gerlach analyzer down, and instead of sending the output of the one to spin down to a counter, I send it to a Stern-Gerlach analyzer and then set up the counters this way, we get sort of, again, the same thing we would expect. So if I send 1,000 particles through there, again, the first Stern-Gerlach analyzer sends half of them are spin up and half of them are spin down. If we then measure the spin down beam for the z component of its angular momentum, we get all of those are spin down beam, all of them measure as spin down. So again, nothing very unusual in the way what we might expect for an experiment like this. All right, if you measure it once and then you measure it again, you get the same sort of thing. A little bit of terminology. We're gonna refer to this first Stern-Gerlach analyzer sort of as a state preparation. What it's doing is state preparation. We have essentially an unknown sort of state coming in, and what this does is it allows us to know the states coming out. So it's prepared this beam, the upper beam, as a spin up beam, and this one as a spin down beam. So this is what we're doing here is we'll call it state preparation. So if we prepare the beam in the spin down state and then measure spin down in the z component of that spin angular momentum, we get everything that comes in is spin down, which again is what we might expect. So that's the first experiment we're going to look at today. Nothing too unusual yet. Experiment 2 is going to be very similar, right? So let's reset our counters. The only difference is we're going to take this Stern-Gerlach analyzer, and instead of measuring the Z component of the spin angular momentum, we're going to look at the X component, right? And if we look at a particle at a time, see spin down in the Z direction, and it was measured as spin down in the X direction as well. Spin up gets counted as spin up. We keep going like this. We do, say, another 1,000 of those. And what we notice is half of the particles in the state preparation in the first Stern-Gerlach analyzer come out as spin up, and about half come as spin down. Of those spin down in the Z direction, those are further split 50-50, spin up and spin down in the X direction. Nothing really too surprising here, right? When we prepared the system in the Z direction, there's no reason to think that tells us anything about the X direction either. So since this oven threw out a bunch of random, states, we have an up and down in the Z direction, but we would still expect, since we haven't done anything with X to be totally random, and it's 50-50 up and down. So that doesn't seem too unusual. Again, we could have switched this and sent the up beam to there and just switch which beam's going. And you'll notice if I send 1,000 particles, it's the same thing no matter what the input beam is. No matter whether it's spin up or spin down in the Z direction, if we send that to an X analyzer, we get about 50-50 output. So now I've reset the counters and I've cleaned up the paths that these beams are taking. Now we can move on to the third experiment I want to look at. So we prepare the system using the first Stern-Gerlach analyzer measured in the Z direction. So we have a spin down in the Z direction going into this X Stern-Gerlach analyzer. And I want to add then another Stern-Gerlach analyzer, this time measured back again in the Z direction. And what we're going to pay attention to here, if I can just add these counters, I feel like I'm running out of space. Let's move this back a bit. What are we going to get as a result of this? Sorry. So again, let's just walk through what we've got here. We've got state preparation, the first Stern-Gerlach analyzer measuring the spin in the Z direction. We get spin ups going to a counter, spin downs going to a Stern-Gerlach analyzer aligned in the X direction. And last experiment, we saw that that's going to split this beam 50-50 up and down. We send the spin up in the X direction into this Z Stern-Gerlach analyzer, and it's going to count how many spin up and spin downs it are. Now, let's just do this, all right? So if we do one at a time, actually, let's just do 1,000 and see what we get. Let's do another 1,000. Keep going. 10,000. We do a bunch, and what we end up seeing, what we have here is, all right, if we look at the first Stern-Gerlach analyzer, we get exactly what we'd expect. Half go up, half go down. We send that into the X, and we get about half of those. So 64 went up here, 6,400 or so went up here, 64 went down. Half of those went down. The other half went out the spin up in the X direction. So now we have roughly 3,200 spins that have been previously measured as spin down in Z, then spin up in X, and now we're measuring them in Z again, and they're split 50-50 again. This is sort of one of the first this isn't making sense with our sort of classical intuition, right? We already measured the particles coming this way as spin down in the Z direction. How are they not all still spin down? Right? This isn't, an engineering issue, but somehow measuring the X component of our spin angular momentum made it sort of forget or, erased, or however you want to think about it, the fact that they were previously measured as spin down in Z, and now it's just totally random whether they're up and down in Z again. And this is, again, really a counterintuitive thing. Somehow this measurement here that we performed with the second Stern-Gerlach analyzer sort of screwed up our knowledge of the Z component of that spin angular momentum that we had previously measured. So now for the fourth and final experiment that we're going to look at today. I'm actually going to do 3 different experiments, but the first 2 are just to sort of highlight how weird the third result actually is. So the first 2 are just variations essentially, or exactly what we just did, where we have our 3 Stern-Gerlach analyzers aligned in Z, then X, then Z. The first one is just preparing our beam in the spin down in the Z direction state. Measure that in the spin X direction. It splits it 50-50. Then measure the final spin projection or spin component in the Z direction. And what we just saw is, send 1,000 through. 100% of our beam comes here. It's roughly 5,000 particles. That gets split 50-50 in the X direction. And of the 25,000 particles or so that we're looking at here, half go up and half go down. So about 25% of this initial spin down beam coming into the X get measured as up or down, right? I can reset that. And if I wanted to, and I do, I'm going to just switch which beam coming out of my Stern-Gerlach analyzer in the X direction is going into my third Stern-Gerlach analyzer and run it this way. So exact same setup. It's set for 100% of my beam is spin down, measured as spin down in the Z direction. It's my input into my X Stern-Gerlach analyzer. And if I then take the spin up out of that X Stern-Gerlach analyzer and put it as my input into my final one, I get essentially the same thing. Roughly 5,000 particles going into this X. Half of them go to my final Stern-Gerlach analyzer, and that splits that half again into half of them spin up in the Z direction and half of them spin down. So again, 25% of my initial beam going into my X Stern-Gerlach analyzer is measured as spin up or spin down in the Z direction. So for the final sort of measurement in the series of these measurements is what I'm going to do is reset all the counters. I'm going to get this beam, and instead of sending it to its own counter, I'm going to just bring it back together with the other output beam. So we have both outputs of this X Stern-Gerlach analyzer going into the Z Stern-Gerlach analyzer, the final one again. There is, so in practice, actually doing this coherently, which is what's required for this, it is quite difficult, but it can be done. But that's the beauty of this SPINS virtual lab, is we can just do it by connecting some lines. What do we get when we run this? Keeping in mind, if I only sent the up, if I sent the spin up, the beam measured as X spin up into Z, I'd have 25% of my beam measured as spin up, 25 as spin down. If I sent just the bottom one, I would have, again, 25% of my beam spin up, 25% of my beam spin down in the Z direction. Now, if I send both, what would we expect to get here? So let's just send a few thousand through. So there's 20,000 particles. And what do we get? All of the results, all of the measured results of our beam are all spin down what the initial beam was there, right? Now, if we think about it, this is kind of crazy and warrants some more detailed thought about what actually is going on here. So let's look at what we're actually getting with these results. So this is what the first experiment of that series was. And what we had is, if we send our beam into this X Stern-Gerlach analyzer, half of it would come out the spin up output, and we send that into this third Stern-Gerlach analyzer aligned in Z, we'd get a quarter of our particles here, a quarter of our particles here. So for the first experiment, the probability of finding a spin up was 1/4. And the probability of finding a spin down in that first experiment was 1/4 as well. Okay, if we look at the second experiment, experiment 2 in that series, we find the same sort of thing, right? The probability of experiment 2 measuring it as a spin up was 1/4, and the probability of experiment 2 measuring it as spin down was 1/4. So in the third and final experiment, in experiment 3, what we did is we basically combined both experiment 1 and 2. You know, you think about it, we have this beam with 100% of our particles going into X. We take both the outputs, which is essentially the top one was experiment 1, the bottom one was experiment 2. If we put them both into our final Stern-Gerlach analyzer, what we might expect is the probability of experiment 3 measuring spin up should just be probability of experiment 1 measuring spin up plus the probability of experiment 2 measuring spin up. So we would expect this to be 1/4 plus 1/4, or a half, or 50% of our beam would be up, and likewise for spin down, we would expect this to be a half as well, just by adding the probabilities from these two experiments. Clearly, this is not what we see, right? So this sort of probability analysis doesn't make sense here. As much as this doesn't make sense, we've actually seen something like this before. If you think back to the double slit experiment that you probably saw in one of your previous courses, essentially, if I shine light at from a point source at a screen with two small slits in it, and I see how that shines the resulting intensity of that light on a screen that's projected onto, what do I see? Well, if I only have one of the two slits open, I would just see sort of this broadened intensity distribution like this. If I had the other slit open, I would see a broadened intensity distribution centered around that slit. But if I put them both open, we get this interesting interference pattern. And that's the same sort of thing, where if only if you look at the minima in that interference pattern, if I looked at just one of the slits open, it would be brighter in that spot than if I have them both open. And the way that works, or how we accounted for that, is essentially what we do in these optics experiments is we take the electric fields from that are reaching there, those waves, and we sort of superimpose them. We just add them together to get the resulting electric fields, and then we square that to get the intensity. And when we square that, we get these cross terms that can result in these interference effects that actually reduce the intensity over just adding those two. And what we're going to see in future lectures is that we get the same sort of thing in these quantum mechanical systems, where what we're going to do is we're going to add these sort of state vectors, these probability amplitudes together, and then when we square it to get the actual probabilities of a final state, we have these cross terms and this interference sort of effect that can come in that leads to some really interesting things. And we're going to start working on that in the next video.